Hi, I'm Kim Shepard again. This is video 2B. Today we're going to talk about graphing. When you're graphing data, one of the first things that you want to look at is the type of variable that you have. So we need to pay attention to whether the variable is a categorical variable or a quantitative variable. If you're graphing a categorical variable, we have two graphs that are appropriate. One would be a bar plot, and the other would be a pie chart. So if we have something categorical, like the make of your car, we could put that graph in either a, or put that data in either a bar plot or a pie chart. There's some examples. This obviously is a pie chart. This is gender of Cecil College students. So the large portion of the pie denotes the female students. We can see there's a lot more female students. The smaller section is the male. So this would be the categorical variable gender, displayed in a pie chart. Here's a second categorical variable. This comes from the General Population Survey of 2008, where we look at people's marital status. So your marital status, you're married, you've never been married, you're divorced, that's a categorical variable, and so this information is displayed in a bar plot. One thing to note with bar plots, when we create them in StatCrunch, by default they'll be listed down here just in alphabetical order, so actually this divorced bar would be over here. This displays a little bit nicer with the bars sort of going in descending order of the percentage. But since this variable is categorical, there's no reason why we couldn't pick up one of these categories and move it. This is not a number line down here. So you'll also notice there's a little bit of space in between the bars on a bar plot. We'll see a difference when we get to a graph for quantitative variables that also contains bars. So if we have a quantitative variable, a numeric variable that has numeric value, our choices for graphs, we will not make bar plots or pie charts. We'll make histograms, dot plots, and box plots. So our choices are histograms, dot plots, and box plots. And again, we'll show you some examples of each one of these. This is a histogram. So this time we have a quantitative variable, and we see down here on the x-axis that this is whatever variable it is that this is a graph of. One thing to note, this graph doesn't have a title, so I'm not sure what the variable is. I'm going to make this up and say that this was perhaps scores on a test. So one thing to correct about this, we want to write an appropriate title to this. So maybe these are test scores or something. So I'll add a title to that. Test scores would be a quantitative variable. And so this looks similar to a bar plot, but very different. This is called a histogram. Obviously, here are the test scores down here. I could not pick up a test score of 80 and move it in front of 20. That doesn't make any sense. This is, a numerical number line here. So you'll also notice that if there are test scores in adjoining groups here, that the bars don't have a space between them. We can't move those bars around. They're stuck on that number line. This groups data in different sort of classes here. I can see that there were several test scores between 80 and 85, but I can't see individual test scores in a histogram. So I have no idea if there was anyone that scored, say, an 82. But this is a nice visual display of the quantitative variable test scores. A second choice would be a dot plot. This plot has a nice title, and here we're looking at two sets of information on a dot plot. We've got production downtime for both the day shift and the night shift, and these are times in minutes. And so the advantage of a dot plot over a histogram, it doesn't look quite as savvy, but we can see the actual individual observations here. So if I want to know at the night shift, was there ever a downtime of exactly 30.6 minutes, I can see, yes, that time actually occurred 4 times. So a second option for graphing a quantitative variable. Our third option is a box plot. Here we have two box plots. So this box plot is whatever A represents, this one's whatever B represents. And again, what's missing? I don't know quite what to talk about with this one because I don't know what was graphed. So clearly a title is missing here. So perhaps these were test scores again, and maybe this is Kim Shepard's class and this is Joe Cooper-Sennon's class, and we're comparing test scores. So a proper title here would be better. And it'd be nice to know what A and B is. I'm going to say this is Kim's class and this is Joe's class. And with a box plot, you'll learn more about the details of this later, but we can see where the median is. That's where the straight line is here in the middle of the box. You can see where the values ranged from. We had some outliers that are denoted with dots. You'll learn more about the details of those later. But this is nice to compare how, say, two classes did on a test. So a box plot is a third option for graphing a variable that's quantitative. Okay, one of the things that we will see with all graphs should follow what's called the area principle. And the area principle simply states that the area of your graph that's represented by something should be true in that graph. So for the Cecil College example, if 2/3 of the students are female and we make a graph to visualize that, then it really should be that 2/3 of that pie shows that the students are female and the other 1/3 of the pie should be male. If you check out publications once in a while, you can sort of catch them where they say 50% of something is this, and if you look at the bar, it really didn't go up to 50%. So we want to make sure that that area principle, that our graphs truly represent what we are displaying information on. To avoid violating the area principle, we strongly recommend that you avoid 3D graphs, three-dimensional graphs. Microsoft Excel has a lot of these. When you start to introduce the third dimension, this piece of pie is only supposed to represent 9.7%, but by adding that third dimension, often that can distort the proportions and throw that area principle off. So we want to avoid three-dimensional graphs, just nice, simple, basic graphs where the area principle there is kept intact. So often those three-dimensional things can make things look a bit more inflated or deflated than they actually are by adding that. In our class, in Math 127, we're going to be using StatCrunch to make all of our graphs, so you'll learn about that. In class, occasionally we'll draw a graph by hand, but anything that you turn in for this course, you'll be creating in StatCrunch. All of our graphs should include informative titles, which we've seen ours violate a couple times here, so be careful to make sure that you have a title on your graph, otherwise I might not know what graph we're looking at, and the axes should also be labeled when appropriate. One caution about StatCrunch, there's no default titles in StatCrunch, so you have to add those. We'll show you how to add those, it's very easy. But make sure your graph has a title so we know what we're looking at. Again, we'll access StatCrunch very soon in class, but when we do, there's a data set on our group page called General Social Survey 2008, where researchers surveyed 2,023 Americans and asked them a variety of questions from their race, their marital status, do you favor the death penalty, and how religious are you? The data set has over 60 variables. Some of the variables are categorical, some of the variables are quantitative. And so let's look at a few. This is a graph of marital status. And so I think we've seen this graph in a previous slide. No one falls into more than one category. You have to be either married, never married, divorced, widowed, or separated. One comment, our graph should have a title, right? So make sure you include a title on your graph here. All right, what are we to answer with this one? Approximately what percentage of respondents were divorced or separated? Okay, if we come over to divorced, here's the percentage that were divorced, and if we sort of eyeball that, somewhere between 10 and 20% were divorced. I think that's a little bit below 15. I'm going to approximate this as about 14% were divorced. If we look at separated, that's this last category here, and if I sort of eyeball over where I think that was, again, I think that's just below 5%, so I'm going to say this is approximately 4%. So what percentage of respondents were divorced or separated? If we combine those two, 28% approximately. Not really an exact answer here, but we approximate that about 28% of the respondents to this. Ooh, not 28. I'm adding 14 plus 14. Thanks. Correction, in addition to the title, right? Let's do the basic math. Sorry. 18%. I make mistakes too. Thanks. Okay, 18%. That's better. Were divorced or separated. Whoops. All right, let's go to the next one. See if I can do the easy math a little bit better. This one's a little bit harder too. Give us your best estimate for the number of people in this study who were divorced. All right, notice the difference in this one. Number of people. Over here, we've got the percentages of people. So last time I could just look up those percentages, and I could have just summed them together. In this case, we actually want to know the number of people. So first, let's look at the percentage of people that are divorced. So if we look at that, let's see, what did we approximate this to be? We approximated this to be 14% in the last slide. But that's not what we want to know. We want to know the number of people. So we have to recall that in this data set, this was based on 2,023 people. So out of 2,023 people, 14% of them were divorced. We want to know what 14% of 2,023 people is. Of, you multiply. So I need to multiply this by 14%. In your calculator, you can type that in as 0.14. And if you do that, we get that this is approximately, I'm going to cheat now so I don't get this wrong, 283 divorced people. So a little bit of a different question than what percentage. If you wanted to know the actual number, take that percentage, multiply by the total number of people in that data set. Okay, a couple more. Okay, this is another bar chart. We're still looking at marital status, but this time we've introduced a second categorical variable, which is race. So this is called a stacked bar chart. We're looking at the distribution of marital status broken down by race. So within each race group, we see what percentage were divorced, what percentage were married, never married, separated, and widowed. This is a little bit tough to see up here, so I'm going to attempt to draw a line between the bottom two categories here. That's why I can't say it. This category was white. This just continues down. So the bar chart really extends all the way down. You see that in your notes, that this bottom category, these are the divorced folks down here. Okay, so what do we want to know in this one? What percentage of people are married within each race? Okay, so married was the second category. For the race white, that's the people that are right in here. And so we want to know what percentage of the people that was. So we sort of have to approximate where this starts and where this ends. This, I probably drew that up a little bit high, but this looks to be maybe around 16%. So 16% were divorced, and then the married part of this starts at 16% and extends up to not quite 70. I'll say maybe 67%. And so if I subtract these two, then we'll know the percentage of people that were married within the race category white. So white married, let's subtract. every time. About 51% of the people that are white were classified as married. Same thing within the next bar. Whoa. This bar looks to start here at about a little bit less than that bar, maybe around 14%, and extends up to just over 40, so maybe about 43%. So again, if I subtract these two, I can see what percentage of the people are married that are in the black race category. So black married. Ooh. I'm going to have to switch to the regular pen. And here we get about 29%. And then finally, if we go to the other race category and look at the percentage that are married, this appears to start down maybe slightly under 10%, maybe at 8%. This would be up maybe just above 50, maybe around 52%. And these are estimates. If you estimate this is 9% and this is 51% or 53%, that's fine. These are complete estimates. But for the other race category, the percentage that are married, if we take the difference between 52 and 8, we're approximating that about 44% are married in that group. So the percentage that are married varies by their race. They're not all the same. We could have done that for any of the categories. We just happened to pick married for this one. So I think we've got one last question. Are the two variables independent of one another? So two variables are independent of one another if one has no impact on the other. So we want to know if race is independent of marital status, and why or why not. We saw on the last slide that depending on your race, there were a different percentage that were married. All the percentages weren't the same. So it does appear that race and marital status are dependent, that they are not independent. It looks like race affects the likelihood of you whether or not you're married or fall into one of those categories. If the variables were independent, we would expect these stacked bar charts to look very similar, to have a very similar percentage that were divorced, to have a very similar percentage that were married, and you can see there in the married category, you know, that those were very different as we move up here too. So in this particular case, we would say that these two variables are not independent. I'm going to end with a regular marker here. Of marital status. And there were far more married people in the white race category than they were, say, in the black race category, and those percentages were not the same. If race didn't have an impact, again, we would expect those percentages to be approximately the same. We expect the three bars to look almost the same. We'll look at some other examples later where we'll see two variables that are independent of one another, where one variable doesn't affect the likelihood of the other variable. That's it for this one.